Hi everybody, and welcome to Chem Talk, where today we will be going over ionic bonding and running over some examples of it in chemistry. So let's talk about it. Let's begin with a simple definition of an ionic bond. An ionic bond is defined as the complete transfer of electrons from one atom to another, forming both a positively charged ion and a negatively charged ion. A common way to draw it is like this. So we have an anion, which is a negatively charged ion, and this gains electrons. And the cation is the positively charged ion, and it loses electrons. To determine whether or not an atom will gain or lose electrons, one can pay attention to its electron configuration. Ionic bonds tend to form between a metal and a nonmetal. Looking at the periodic table, the metals consist of groups 1 through 12. The alkaline earth metals will most commonly form +1 and +2 charged ions by losing either 1 or 2 electrons based on the number of electrons in their valence shell. However, the transition metals are a bit trickier, as the charge of the ions they form can differ quite a bit. But it's easiest to remember that the metal of the compound will almost always have the positive charge and lose electrons. If the atom has more than 4 electrons in their valence shell, they will most often gain electrons and have a negative charge as an ion. This is often going to be in groups 15, 16, and 17. You'll also often find that group 13 forms a +3 charge with its 3 valence electrons. Now let's discuss how to determine the charge of an ion. What is done most often is to first identify whether the atom is going to lose or gain electrons, based on the methods that I mentioned earlier. The next step is to identify how many electrons are going to be lost or gained. This is done based on the number of electrons in the valence shell of the atom. Let's take rubidium as an example. This has 1 electron in its valence shell. In order to get a complete octet of 8, it must lose that 1 electron, so it will obtain a +1 charge. Now let's use sulfur as an example. This is a nonmetal, so we know it's likely going to gain electrons. Sulfur will gain electrons and form a negative charge because it has more than 4 electrons in its valence shell. It has 6 to be exact. So we do 8 minus 6 equals 2, so it is missing 2 electrons to complete the full octet. This means it will gain 2 electrons and form a -2 charge. Now let's move on to discussing how many of each atom is needed to form an ionically bonded molecule. For example, calcium bromide is CaBr2 and needs 2 bromides for every calcium atom, and we're about to learn why. Consider the electron configuration of calcium. Note how it has 2 valence electrons in its valence shell, so we know it must lose those 2 electrons and gain a 2+ charge. But looking at bromide, which has 7 electrons in its valence shell, it must gain only 1 electron to have a full octet of 8 electrons in its valence shell. So we have a calcium that's ready to give up 2 electrons, but a bromide that will only take 1 of them. To solve this, we add 2 bromides, thus becoming CaBr2. In most ionically bonded molecules, the net charge must be 0. With 1 calcium ion, you have a 2+ charge, and 2 bromine ions provides a -2 charge, canceling each other out and giving us a net charge of 0, which is exactly what we want. Let's do a practice. Think about the molecular formula for barium phosphide. Okay, let's first identify the cation and the anion. Barium is in group 2, so we know it's a metal and is going to lose electrons. Thus, it will be the cation. Phosphorus is in group 15, so we know it has more than 4 valence electrons and will gain electrons to complete its octet. So phosphorus will become the anion. Since barium has 2 valence electrons, we know it must lose those 2 electrons in order to have a complete octet in its valence shell. So barium will have a 2+ charge. Phosphorus has 5 electrons in its valence shell, so we do 8 minus 5, to determine it must gain 3 electrons to complete its octet, and will have a 3- charge. Now, notice how we have one losing 2 electrons and one gaining 3. So in our molecular compound, we aren't going to have a 1-to-1 ratio of barium to phosphorus. There's a handy little trick for determining how many of each ion is needed to balance out the charges. Start by writing each atom with the charge it will have as an ion. Then, underneath, write the atoms next to each other again. Now take the charge of the right atom on the top and place that number underneath the left atom on the bottom. Take the charge of the left atom on top and place that number underneath the right atom on the bottom. So now we have Ba3P2, and 3 barium ions gives you a 3 times positive 2 equals positive 6 charge, and 2 phosphorus ions gives you a negative 6 charge. Negative 6 plus 6 is going to equal 0, so we have successfully balanced the charges of this ionic compound. Now let's try a practice with a transition metal. Transition metals can be trickier since these metals can often take on multiple charges. The best way to identify what charge the transition metal has is by looking at the written name. For example, copper 1 chloride. That 1 indicates that the copper will have a +1 charge. Now, since chlorine is missing only one electron to complete its octet, it will have a -1 charge, and the compound simply becomes CuCl, copper chloride. One other interesting fact to note is that the higher the charges are of the ions, the stronger their bond becomes. There are other factors that contribute to this, like atomic size as well, but that's a whole different topic. In an ionic bond, electrons are completely transferred from one atom to the other. Now, in reality, a complete transfer of electrons is pretty rare, but we just call it a complete transfer for simplicity. The anion is the ion with the negative charge, and the cation is the atom with the positive charge. A helpful tip is to use the crossover method when there is not a 1-to-1 ratio of the charges. Metals will mainly lose electrons, and nonmetals will mainly gain electrons in ionic bonding. So that is all for today on ionic bonding. Thank you for tuning into Chem Talk. Make sure to visit our website, www.chemistrytalk.org, for hundreds of general, organic, and biochemistry articles.